Okay, let's just summarize a little bit what we did in last lecture. So now in the end, we try to say that we can use S and T matrix to label a different topological order. And then we can have some condition on ST matrix so that this ST matrix indeed label topological order. So by solving those conditions numerically, we are able to produce this table, and which presumably, okay, this table should contain all the bosonic topological order, and but because the theory is not totally proven, so this table may have fake entries, and maybe a single entry of this table may correspond to several topological order. But I don't think that's going to happen, at least for those simple one. Maybe for the very complicated one, maybe that happen, we don't know. But that would be maybe some future research project. Yes?
But if I take two systems and find that they're in different classes here,
they are definitely different, yes. And in this table, this D is a quantum dimension of the topological excitations, and S is the spin of those topological excitations. So this is 2, 3, 4, and etc. just to say how many topological excitation we have, how many type of topological excitation we have in those topological order. Certainly, we always include the trivial one. So you can see the first one is a trivial excitation with a 0 spin. That's a boson. So that's a kind of trivial. But the other are non-trivial. Okay. And actually, there's a lot of familiar thing. After Nick's talk, now we can put in some wave function like this is the bosonic Laughlin wave function. So this corresponds to this particular topological order with a trivial particle and a semian. This is quarter spin is a semian. So that's a filling function 1/2 Laughlin states. And then this one, we have four topological excitation plus, including trivial one. And so this is this one. And I think I'm right. And so you have this but this spin is mode, it's only mode 2. So mode 1. So when the spin is more than 1, it's just mode 1. So you get this a little funny related. But Nick talked about this Pfaffin state yesterday, and these Pfaffin states have this wave function. Right down here is a PO paired wave function multiplying a gestural factor, and this Pfaffin wave function, this Pfaffin state corresponds to this particular one. So it have this fermion. This is the Pasai in the Andre's talk, and this is the sigma. This is a sigma is this one. Okay. And then there's a SU2 level 2 states, which I briefly mentioned last time. And this wave function is pretty simple. So we start with a filling fraction 2 fermionic many-body wave function. And this is anti-symmetric many-body wave function with a 2-field Landau level. Then we just square it. When you square it, you get a symmetric many-body wave function. And that is a bosonic, something bosonic. And it turns out that this is a non-abelian state. We call the SU2 level 2 non-abelian states, which happen to correspond to this entry.
Is there a monohamiltonian?
Yes. And there is an ideal Hamiltonian for this wave function. And the ideal wave function is the following. Ideal Hamiltonian is the following. When you square this wave function, you find that the boson can be in first 3 Landau level. So therefore, you have this kinetic energy such that the first 3 Landau level happen to have the same energy. Then you add a delta potential interaction to enforce the second order 0 because you square it. And that's it. That is the ideal wave function, ideal Hamiltonian such that this wave function is the exact ground state of this ideal Hamiltonian. And if you believe this ideal Hamiltonian gapped, then that Hamiltonian would realize this particular non-abelian states. So the unusual requirement is that the first 3 Landau levels are degenerate. This is a little bit unusual. Or you can say that, now people talk about the Chern insulator. If you have a Chern band, which is kind of more or less flat, but with Chern number 3, that would do the job. You can also using that way. And then this entry actually is we call the SU2 level 3. It's a very similar construction, but you start with a fermionic wave function with the first 3 Landau level field. Then you square it, get a totally symmetric wave function, and that is a SU2 level 3. That's another non-abelian state. And this label SU2 level 3 really basically say that the edge state is related to SU2 level 3, more or less. And so this Kasmuni algebra, so that's kind of non-abelian. And that's one thing. Then another thing I like to mention is that, in Andre's talk, there's about this Z16. This is Z16. So what is this Z16? So, the Z16 classification was discussed in respect to some kind of a fermionic topological superconductor or quantum Hall insulator, something. But here I want to give an alternative interpretation of this Z16. The first, Z16 is a classification of a bosonic topological order. Means it's a classification of a topological order in bosonic system. This is Z16. And then it's not all bosonic system. It's a very special bosonic topological order which contains fermions. So that's the second thing. It's not just classification of bosonic topological order. Z16 is a classification of a topological order, bosonic topological order, which contains fermions. But that's not all. Actually, this bosonic topological order not only contains fermion, it's a minimal bosonic topological order which contains fermions. And that is Z16. So what do you mean minimal? Minimal really means that this fermion have a non-trivial mutual statistics with every other topological excitation. So that's what we call minimal. So if you think about bosonic topological order which contain fermion, and this fermion have non-trivial mutual statistics with every other topological excitation. And this kind of bosonic topological order is a Z16. And so which is this blue entry here. So this blue entry happen to be the bosonic topological order which contain fermion, and it's a minimal bosonic topological order which contain fermions. Minimal is defined by mutual statistics. Yeah. So that's another interpretation of this Z16. So if you really say how one derive Z16 from mathematical framework, this is the way to derive this Z16. Yeah. So that's a comment. Yes.
I have a question about your procedure for doing the thermodynamic limit from the.
Yeah.
So what if so you have this equivalence class of Hamiltonians where you carried out some short range entanglement?
Yes.
But what if your hypersis is very small, and then even your short range entanglement is sort of the same as long range entanglement?
Yes.
And then it sort of connects.
That's true.
And then you can from the small one you can build up.
Yeah.
But then secretly they're all sort of part of the
Yeah.
same.
So this is a very, very good point, is that the topological order is not a concept of finite system. It's a concept of a sequence of a Hamiltonian whose size go to infinity. So it's a concept of thermodynamic limit. So as you said, if my sequence stop at the finite size, all this collapse. There's no such thing. And, but we do need an infinite sequence. And this topological order is a property or equivalent class of this infinite sequence. So we have to take a thermodynamic limit. Otherwise, all this do not work. Yeah. Other questions? Yeah. Okay. So using the very similar approach, again, starting with SNT matrix, actually one can get some new result, which is a classification for fermionic topological order, which is topological order in a fermion system. So that's a very different mathematics. For the boson system, the mathematics is so-called modular tensor category theory. And here there's something I just learned last month. It's a modular braided fusion category over some kind of symmetric braided fusion category. But here, this symmetric braided fusion category has to be the representation category of a Z2, but with some twist. Now, I don't know, it's a lot of words. But the twist actually is following. You know, the representation of Z2 just have a two, trivial one, non-trivial one. This twist means that we just think non-trivial one have a spin 1/2. It's a fermion. If you think this non-trivial representation as a bosonic, this will be just standard rep 2. And if you think this non-trivial representation as a fermion with a spin 1/2, that's where the little s means. But that's also a category, and there's something like a category over category, so some notion. And so if you using this kind of framework, you can obtain a different set of condition on SNT matrix. So condition on SNT matrix are similar, but with some modification. And with this modification, you can just do a similar numerical search and produce this table. And maybe look at this. This table really means that the most fermionic topological order we find is actually can be viewed as a stacking of trivial fermion topological order, which is a fermion product states. So this F0 is a fermion product states, which is trivial one, is the first row is a trivial one, stacked with some bosonic topological order. So those symbols, this is 3B, etc., appear in the previous table. So mostly just stacking. And for the simple one, only this one is not stacking. So this is kind of primitive, not the stacking of fermion product state with a bosonic one. And but this one is kind of a Z6 parafermion, maybe a quarter of Z6 parafermion theory in some sense. Yes.
This table could also have some empty spots and degeneracies, right? Are you also using a similar technique like this?
Yes. Yeah. So yes, there could be. We have similar qualifier. That is, there are maybe fake entries, and there's maybe one-to-many correspondence. Yeah, that's we have a similar drawback. Yeah. So yeah, but one can get something. And I want to make another remark here is that this particular entry has been discussed before. If you look at this statistics, you know, 1/2 is a time reversal invariant, and the quarter and the minus quarter is time reversal invariant pairs. So from Borg point of view, these statistics satisfy time reversal symmetry. But however, the chiral center charge is quarter, which kind of the boundary is not time reversal invariant. But however, this one you can say the time reversal symmetry have an anomaly. So actually, this particular 2+1 dimensional topological order can appear as a time reversal symmetric boundary state of a 3+1 dimensional topological insulator of fermions. So this is one of, I think there's a paper which makes this proposal. So this happens to be this particular non-abelian topological order. So that can appear as a time reversal symmetric boundary of a 3+1 dimensional topological insulator, which have a time reversal symmetry.
What are the values?
Oh, this is just a rational number. Because of space, I didn't write down. It's a ratio of a sine divided by sine, with but this happens to be the quantum dimension of parafermion theory. If you look at the parafermion theory, you see their quantum dimension is always a ratio of 2 sine, and with 2 integer entries. So this zeta just that one. Yeah. So whenever you see the zeta is remind you of parafermion. So they have to be the quantum dimension of parafermion theory. So then you can look. So maybe those states are really parafermion. So this is really parafermion. It's kind of like a Z10 parafermion. This is related to Z10 parafermion. You know. So yeah. So mostly it's parafermion theory. It's like this Z2 parafermion. So mostly it's coming from parafermion theory. Okay, so this is what kind of summarize what we did last time. And so today we'll try to add symmetries. Okay, So far, we consider local Hamiltonian, not thinking about the symmetry, so no symmetry at all. So now we add symmetries. So when we add the symmetries, our definition of a gapped phase is changed. The reason is that, in the definition of gapped phase, we have this local unitary relation. We say two Hamiltonian are equivalent if they are different by local unitary transformation. But when you have a symmetries, then you require not only Hamiltonian have a symmetry, that's our input, we say Hamiltonian have a symmetry. So how do you know two symmetric Hamiltonian are equivalent? Then our definition is that we only use so-called symmetric local unitary transformation. So this corresponds to when you do deformation of Hamiltonian, we only deform within the subspace of a symmetric Hamiltonian. So when we do deformation, we keep symmetry, we do not break symmetry. So if you only consider this kind of deformation, then that's really trying to say that the local unit transformation should also have the symmetry. So therefore, these equivalent relations are smaller. So each class are smaller. Then we have a more class. That's basically it. Certainly, we're also using this adding the product states. But certainly, similarly, the product state we want to add should also have a symmetry. For example, if you have an SO3 symmetry, then you want to add this kind of product state of simply spin up, spin down dimers. That's also product state, but also keep the SO3 symmetry. So it's very similar, but because symmetry constraint, our equivalence relation are smaller, and then there's a more class. So naturally, we still have a long-range entangled state and short-range entangled states, but when you add the symmetry, then we have more class. Yes, sir. So this more class we call the symmetry enriched topological order. So that's more class. Yes.
Why didn't the short-range entanglement break?
Yeah. So naively, one would say, yeah, the short-range entangled states is product states. It's pretty trivial. And you do the symmetry, you just have a symmetric short-range entangled state, and that's it. But actually, that's not the case, exactly as you said. Actually, even product states break up into several different phases. So this is a little bit of surprise. It's easy to say long-range entangled state with different class with symmetry, that's easy. But even short-range entangled states break up into many classes. And this is possible because of following. For the Hamiltonian describing those states, they are short-range entangled means that we can using local unitary transformation to change this Hamiltonian into some kind of trivial product state Hamiltonian. But however, if you require the local unitary transformation to be symmetric, then you can have some Hamiltonian which cannot be changed to the product state Hamiltonian under symmetric local unitary. It's doable using local unitary that breaks symmetry, but not doable using local unitary which have a symmetry. So because this reason, so this also break up. And this is so-called symmetry protect topological states. And its definition is that it's a state with no topological order, but protect by symmetry. So we should call that symmetry protect trivial state because the emphasis is no topological order. So maybe you can say the topological bar states, whatever. And then clearly, this state will be the simplest. If you want to understand something, we want to understand something really simple, start with something simple. And this is hard, and we still don't know how to do it. But this looks like should be simple. It's product states with some symmetry. So maybe this is my main topic. From now on, we'll be concentrating on those states. And then the example of those states are really the Haldane phase of a spin one chain, which is a bosonic example for the symmetry protect topological state, SPT states. And the certain topological insulator and topological superconductor and etc., they are the fermionic example of these SPT states. And at the moment, we have a systematic theory for the bosonic SPT states in terms of cohomology and group cohomology. But however, we still do not have a systematic theory for fermionic SPT states. Presumably some kind of a super version of group cohomology, but how to really formulate that, develop that, there's some subtlety. And I want to mention that the Kapustin proposed using some kind of cobordism theory with some symmetry in it, and that could be a systematic theory. But I barely understand the cobordism theory, but with the symmetry, I don't understand, so I don't have too much comment on that. Yes.
Yeah, so maybe it's a dumb question, but so the way I understand those symmetry-rich topological phases is that basically the symmetries, so the anyons form projective representations of the symmetries, and that's why you have those different classes, right?
You mean here?
Yeah.
Yes.
This is one way of looking at it.
Yeah, that's right.
Is it possible to look at those SPT phases in terms of how the symmetries act on the edge states or something like that?
Yes. Yeah.
Okay, so it's something similar.
Yeah, exactly. So you will see that from that point of view, there's no onion in the bulk. So there's no non-trivial excitation in the bulk. So how physical understand these SPT states? Then edge, you can always have defect, which is the boundary. Then the symmetry act in an anomaly way to the boundary. So this SPT actually classify the possible anomalies, but that's a later understanding. So there's a very close relation to the anomaly. So what is a Haldane phase? I just mentioned, yes, a Haldane. Topological literature, I think you heard a lot in the last week. So I think Charles can probably explain that very carefully. But today I will concentrate on the bosonic version for interaction, which this we understand better. So what is this? What is precisely this Haldane phase? And so we can start with a spin 1 chain, okay? And Haldane phase is the phase of a spin 1 chain first. But to really have a picture of the spin 1 wave function, which are disordered, when you have a spin 1 chain, it's easy to see an ordered state, like up and down, that's an antifermionic states. We usually understand that very well, but that's a product state. And the Haldane proposed that actually for spin 1 Hesmer model, the ground state is not ordered. It's a disordered with energy gap. So how to understand this many-body disordered spin 1 wave function? It's not so easy. And but there's a way to do it. Is that proposed by this AKLT? Is I think at that time, I said Affleck and Lee probably is in Princeton. Maybe other visitor of Princeton. So we break this. We view the spin 1 as a 2 spin 1/2 on each side. So each block is a 1 side. We view this as 2 spin 1/2. And then we can certainly project out the spin 0 sector. Spin 1/2 is a spin 0 and spin 1. We just project out spin 0 sector. But when you view as a 2 spin 1/2, then you can form a singlet between neighboring spin 1/2. So this spin 1/2 in one side and this spin 1/2 in the neighboring side form a singlet. So this green bar means a singlet, spin singlet. Then you can build a wave function like that. Now obviously this is singlet, they are disordered wave function. There's no spin order. And then you can, once you build this wave function, you can project out the spin 0 sector in each side. You get a spin 1 state. And this spin 1 state happen to be the exact ground state of this AKLT Hamiltonian. We add this 4 spin term. So that's put the Haldane phase in a very solid exact footing. So there's that's precisely the wave function, ideal wave function. So actually, we don't need to project the spin 0. Project spin 0, not project spin 0 is not totally necessary. So you can imagine we can start with a system where on each side we have a spin 0, spin 1 excitation. Means that each side you have 4 states. They forming spin 0 and spin 1 representation of SO3. So we can start with this kind of a modified model. When you have this modified model, we can really view this spin 0, spin 1 as a 2 spin 1/2, and really just using this wave function as a ground state wave function. And this is even better. So this is a kind of ideal RG fixed point wave function of a Haldane phase. So this spin 0, spin 1 per site, and this ideal wave function for Haldane phase. So we can view the Haldane phase as this kind of a wave function, basically. And then the claim is that this kind of a wave function is different from another wave function of a spin 1-0 chain. That is, on each side, we say the spin 0 have lowest energy and the spin 1 have very high energy. So the ground state are local singlet on each side, a singlet on each side. So this is another disordered ground state of a spin 1-0 chain. And then the claim that this kind of a spin disordered state of spin 1-0 chain and this kind of a spin disordered state of spin 1-0 chain belong to different phase. Although both phases have a gap, do not break SO3 symmetry, but somehow these two phases are distinct. You cannot go from one to another without phase transition. So how I understand that? Well, one way to understand that is when you have open boundaries. You can see for these local singlet states, the open boundary have nothing. But however, for this Haldane phase, the open boundary have this unpaired dangling spin 1/2. So this emergence of a spin 1/2 at the boundary is a sign of this non-trivial phase of matter, which is Haldane phase. And this is certainly we need a symmetry, because if you add a magnetic field to break the symmetry, this spin 1/2 became polarized. We lose the degeneracy. Without SO3 symmetry breaking, each boundary have a twofold degeneracy coming from spin 1/2. But when you break SO3 symmetry, the degeneracy is lifted, and so the distinction between these two phases no longer exists. And also from this picture, it's clear these are short-range entangled states. At least for this ideal wave function, you can see that this is a singlet, this is singlet, but there's no entanglement between this pair and this pair. So it's a short-range entangled. So both states are short-range entangled. It's just but somehow it belongs to different phase. So this is a kind of maybe you can say the canonical example of the Haldane phase in 1+1 dimension, and also the canonical example for the SPT state is the simplest example for SPT states. So any question here? Yeah. So maybe as a remark, this is very similar to this Marana chain discussed by Andre. So this is so there you have a dangling Marana zero mode on the boundary. So that is a 1+1 dimensional example. So now let's give a 2+1 dimensional example. And in a 2+1 dimensional example, we consider the system with a Z2 symmetry. So we're like Z2 symmetry. So how to understand the SPT states protected by Z2 symmetry in 2+1 dimension? And the idea of construction is pretty similar to Haldane phase. So in the Haldane phase, what we did is following. We start with a system with a spin 0, spin 1 on each side. So this form a reducible representation of SO3. Then we split degree freedom on each side into 2 degree freedom, each have a spin 1/2. But each spin 1/2 is not a representation of SO3. You know, spin 1/2 is not a representation of SO3. It's a representation of SU2, but not SU03. Okay. So then we do something. We play a game. We do something. So here we are similar. We start with a representation for Z2 on each side. Then we split degree freedom so that individual splitted degree freedom do not form a Z2 representation. So this is the idea. Okay, so how we do that? So we consider square lattice. So each box is a side of a square lattice. And then on each side, we have 4 qubits. 4 qubits will be a 16-dimensional vector space. So each side we have a 16-dimensional vector space, which is split into 4 qubits. Okay, spin up, spin down. Okay, and then so the important. So let me talk about the symmetry first. The important thing is the symmetry. So what is Z2 symmetry? The Z2 symmetry is a simple. It's just a spin flip. But however, the spin flip is not good enough, because if you do spin flip up to down, down to up, then each individual one will be a representation of Z2 symmetry. And so this is not what we want. We want, as a 16-dimensional vector space, the Z2, that's a 16-dimensional vector space on each side is a representation of Z2. But however, each of these qubits is not representation of Z2. So how to make that happen is this. We can define the Z2 symmetry in a kind of unusual way. So this UCZX is a generator of a Z2 symmetry, which acts on these 4 spins. That's it. And this generator contains 2 parts. This UX part is a spin flip. We just flip these 4 spins. It's spin flip. Then we add another part, this UCZ part. Why we call CZ? That's a controlled, actually controlled NOR gate, controlled 0 gate. I don't know. This is some controlled gate in quantum information terminology. So this the action of CZ is that they do not act on the individual spin. They act on the pair of a spin. So therefore, this UCZ contains 4 terms. So they act on 1, 2, act on 2, 3, act on 3, 4, act on 4, 1. So it contains 4 terms. So each CZ acts on a pair of spin. And they act in similar way. They just don't change the spin, except when you have both down spins, you add the minus sign. So we have when they act on the down, if 2 spins both are down, you just add the minus sign. So this is some kind of a CZ gate in the quantum information terminology. Okay. So because of so therefore, as an operation on 4 spins, this is a Z2 transformation. You can show that the square of this operation equal to identity. So this is a Z2 transformation. But somehow, such kind of Z2 symmetry cannot be realized on the single spin. And so the single spin do not form a representation of this Z2 symmetry. Okay. So this is so this construction is very important. Okay. And if you do that, then you have this kind of unusual Z2 symmetry. And then when you construct then when you just construct a wave function, then you just follow the Haldane's phase. This AKLT idea is that now we pair up the neighboring spins. So here, this is a yellow box is a side. Now we pair up this, not pair up, now we put 4 spins together like this box. This box means we have all 4 down plus all 4 up. Just a superposition of all down and all up. So this kind of entangled states. So on each box we have that. Then that's it. So we just using this black box to means all up, all down. Then on each square you have all up, all down. Then that's build the ground state wave function. Yes.
Is there any reason you use CZX instead of just CZ?
Only CZ. I don't know. Yeah, I have not stopped on this one. If you only use CZ, whether it's something or not, I don't know. Yeah, and I just know this works. And then you can check this particular wave function indeed is a symmetric. So that's this box. This black square really means these states, and it is this wave function is a let me see. Yeah, this wave function is the environment. little bit of some kind of calculation is that you have to make sure that this phase factor cancel out. Because this particular arrangement, because all these four spins point in the same direction, etc., at the end, all these phase factor cancel out. Okay, and so that's it. And then you ask, do we have a Hamiltonian which realize this ground state? The answer is yes. So certainly we have a Hamiltonian. It's very complicated, so I don't want to really go into detail of that. So this Hamiltonian is acting on this four side. So this Hamiltonian, each HP acts on this four side, on this square four side. And it contains a term which is x, a, b, c, d, which basically flip, spin, and up to down. So make this favor this kind of combination in this black square. But it also contain four projectors. So not only prefer this kind of all up plus all down combination on this black square, it also enforce the two spin, these two spin always point in the same direction. And these two spin always point in the same direction, so that's a projector. And so basically some Hamiltonian of this kind of, this sort would select this uniquely this kind of a ground state wave function. So it's a pretty complicated Hamiltonian, but they exist. And this Hamiltonian, I think, is a commuting projector, so it can be solved exactly. Okay, so this is an example of this Z2 SPT states. So there's a very concrete construction. And so certainly you say, so what? You have some state with Z2 symmetry. You know, how do you know this one is non-trivial? You know, how do you see this is non-trivial SPT states? And to see that, we should study the edge states. So, so the claim is that for this particular system, when you have a boundaries, the boundaries are gapless or break Z2 symmetry. So that's only two alternatives. So usually you say there should be third alternative. That is the boundary are Z2 disordered with a full energy gap. So that is a trivial Z2 disordered states. And this third alternative or third option is missing. So this kind of Z2 SPT state have this special boundary which cannot be trivially disordered symmetric boundary. Okay. And in this case, it either has to be gapless or has to break Z2 symmetry. If you want to be gap, it has to break Z2 symmetry. So how to understand that, at least in some sense? So then we just consider this kind of Hamiltonian and look at the boundary. Just look at the boundary. And remember that this Hamiltonian make this all this plaquette to be all up, all down. So all those degree freedom are kind of frozen. They already settled. These are all up plus all down. That's it. They choose these ground states. But however, for these two spin, things are a little tricky because these two spin, we have this term, P term, to make these two spin always parallel. But this P term do not say whether it should be both up or both down. So these two spin can be up or down. And it's not frozen. You know, this up and down are both okay. The Hamiltonian are happy with both cases. So therefore, so we have effective spin on the boundary, which corresponds these two spins up or down. So like this two is down, this is up. So this effective spin on the boundary form this low energy degree freedom on the boundary. Then you ask, what is a Hamiltonian, or what is the symmetry of this on this effective spin on the boundary? And certainly, our whole system have a Z2 symmetry. So the boundary spin should also satisfy some kind of Z2 symmetry. But what is this symmetry? And then we notice that when we have a Z2 symmetry on each side, we have this CZ term between these two spins. It's not just spin flip. It's a spin flip plus some phase factor which depend on these two spins. So now from here you can see that the Z2 symmetry on the boundary is a little bit funny. It's a flipping spin, boundary spin, but also have a phase factor depend on the neighboring spin. So there's a phase factor here depend on the neighboring of a spin. It really is coming from the bulk Z2 transformation. So therefore, that's a key. So therefore, the effective Z2 symmetry on the boundary is not on-site. It's not just flipping spin from up to down, but have this CZ term which is connecting neighboring spin. This is just a phase factor. But this plus or minus sign depend on whether neighboring spin are up and down. If two neighboring spin are both are down, then there's a minus sign. Otherwise, this phase factor is just up. So basically just a spin flip plus some phase factor depend on neighboring spins. And so the key point is that this is not an on-site symmetry. So usually when we say global Z2 symmetry, we also implicitly assume this Z2 symmetry is on-site. They act on each lattice vector space individually as a product. It's like this. So this is the on-site symmetry. But then this Z2 symmetry on the boundary is not on-site. And then you may ask, can I make it on-site? You can choose different bases. Maybe if you choose different bases, you can make it on-site. But however, the answer is no. Actually, certainly by choosing different bases, we should keep this site structure. If you keep site structure, it's just choosing different bases on each side. You can sometimes this phase factor can be removed. But in this particular case, this phase factor cannot be removed. You can modify that, but it cannot be really removed. And and that's it. So this is a non-on-site symmetry if this phase factor is not removable. And this is anomalous symmetry. So you'll say some symmetry are anomalous. What that looks like? Well, it looks like this. So when you say anomalous, people talk about the symmetry in field theory. Sometimes they say, oh, this symmetry is anomalous, cannot be gauged. And so this anomalous symmetry can be put on the lattice if you make it non-on-site. So this non-on-site and anomalous symmetry is the same thing in my understanding. So therefore, the boundary spin 1/2, the boundary this Z2 degree freedom have this anomalous Z2 symmetry. So therefore, the boundary effective Hamiltonian should be invariant under this non-on-site Z2 symmetry. Then clearly, you can write down the Hamiltonian like sigma z. That's a standardizing term. And this term is always invariant under this non-on-site Z2 symmetry. And you can also try to add this magnetic field in x direction. When you add the magnetic field in x direction, you'll find this magnetic field in x direction actually is not invariant. And so usually, because here we flip SZ spin up to spin down. So usually the magnetic field in x direction is invariant. But because it's a non-on-site condition, we find only this combination is invariant under this non-on-site Z2. Yes?
So usually when we talk about an anomalous theory on the edge, there's some associated notion of anomaly for continuum theories. Is there a lattice equivalent?
So you say if you have a anomalous, so let me try to rephrase your question. It says, suppose you have an anomalous gauge theory. Okay. Then you ask the following question. Suppose we don't gauge it. We treat the gauge symmetry as a global symmetry. We just don't include the gauge field. You have same matter field. This is a little bit of a tricky thing. The way I try to say the following is that, when people say gauge theory anomalous, the statement, in my understanding, had nothing to do with gauge theory. It's only say that the matter field, because you can understand this theory is anomalous without introducing gauge field. You can just calculate triangle diagram of a matter field. So this statement is a statement for the matter theory without gauge field. So then you can say, if you don't add the gauge field, only think of symmetry, then you have so-called anomalous symmetry. So when I say anomalous symmetry, it really means you have anomalous gauge theory, but treat gauge theory as a global symmetry. Then you may ask whether a field theory with anomalous symmetry can be put on the lattice or not. At the moment, my answer is yes, but the price you pay is that the lattice version of a theory should have this non-site transformation.
So just as a follow-up, I'm just thinking back to Professor Seiberg's discussion of introducing sort of edge theory to cancel an anomaly in bulk theory.
Yeah.
So essentially, you're saying that so this edge theory is also quote unquote anomalous in some way, and you have some anomaly cancellation. You have to
Yeah.
make the whole theory invariant. Here, the whole theory is invariant, including the.
Yeah. So my point is that you don't need the bulk theory. In this case, you don't need the bulk theory. If you don't gauge it, you can see here we do not gauge this symmetry. We only consider symmetry without gauging it. If you do not gauge it, you have UV completion of a theory without the bulk. That's my point. But however, the UV complete theory, the global symmetry is realized as a non-onside symmetry on lattice. So I think that's kind of a maybe new understanding of this anomalous symmetry. And, but because this phase factor, you cannot gauge it. This is symmetry, we cannot gauge this kind of global symmetry because this non-sightedness. So I think this to Hooft point of view of anomaly, so maybe it's related. It's ungageable global symmetry. That's another way to say this. Yeah. So this is a particular, any other questions? Yeah. So, well, yeah.
You just made your site bigger, you still have an on-site symmetry.
Yeah, this is a very good point. As you know, you may worry about that. You can combine several sites together, whether you can make this phase factor goes away. No, they don't go away. And but I couldn't explain better using this kind of formulation. Yes.
Isn't it clear if you combine two sites?
Yeah.
Each site is linked to both the one below and the one above.
Exactly.
So combining two sites doesn't help.
Exactly. If you combine these two sides, you still have this gap. So this phase factor is, yeah. But the question that if you, more generally, if you can do something, whether you can do it, yeah. I think later when you do field theory, understanding of this is to be clear. It's more clear. This phase factor is not removable. So the reason it's not removable is related to some cocycle. You know, it's not co-boundary, it's cocycle. So it's related to that. Yes.
So the X theory is modular invariant?
What?
X theory is modular invariant?
No, it's this is lattice theory. You know, it's just I don't know what is a modular environment. I mean, if it's maybe it's low energy theory, it's conformal field theory. Maybe there's a modular invariance of the conformal field theory. But this is a lattice theory. This lattice theory even can have a phase which breaks Z2 symmetry. So can be gapped. Yeah, so it's not related to that. And here I just want to say that this is generic Hamiltonian which have this non-onsite Z2 symmetry. But certainly you can study a special one. For example, let's only pick this term. So we can have this particular Hamiltonian like with only magnetic field term. And this Hamiltonian certainly respect to this non-onsite Z2 symmetry. And it turns out that you can do some mapping, non-local mapping. And this Hamiltonian is due to XY model. So this is one way to say that you have an edge Hamiltonian which is gapless. You know, XY model is gapless. Okay, so this and also it's gapless described by a C=1 conformal field theory with both the left mover and the right mover. So at least in one phase of the one possible boundary of this Z2 SPT states is described by this Hamiltonian, and it is basically due to the XY model on the lattice. Okay, so then we can understand from this XY model point of view what happened to the edge. Yes.
If I just start with this Hamiltonian and gauge the symmetry, I know that in the bulk I get double semyon model. What will I get on the boundary?
If you gauge it, and you get the same thing. And what I try to say is that if you modify the model and to couple the Z2 gauge field to the bulk, the bulk, the Z2 symmetry is on-site. You can gauge it. You can couple Z2 gauge field. And when you couple the Z2 gauge field, and then this became a digraph-Witten model, one of a twisted Z2 gauge theory. And the boundary is still seek to so seek to unconformal field theory is still a possible boundary of this digraph-Witten model.
So that coupling procedure doesn't change the boundary, it still remains the same.
The reason is that it still remains the same dynamic because Z2 gauge field is have no low energy effect. But however, this would be really, really interesting example. So there's a way to have to add Z2 gauge symmetry on this axion model, seek to unconformal field theory, such that Z2 is anomalous. Then it's coupled to the bulk digraph-Witten theory in certain way. There's anomaly inflow. I'm not familiar with that, but I think maybe what Natty talk about may be related to this. Yeah. Yeah.
Can you explain again how once you have your bulk Hamiltonian, how do you obtain your H?
Oh, just arbitrarily. We only fix the bulk part. On the edge, you can add any term you want, as long as you do not break Z2 symmetry. So that's why I did not really write down a particular edge Hamiltonian. I just write down any edge Hamiltonian which are consistent with the symmetry. So this is the thing, because we can make an edge in many different ways. So whatever we make, we always produce edge Hamiltonian which are consistent with this non-ansatz Z2 symmetry. So this is one possibility, and this is maybe, if you fine-tune things enough, you probably can get this one. And if you get this one, you have this axion model. And certainly there's an issue, whether for generic edge Hamiltonian, do you get a gapless phase or you get this Z2 symmetry breaking phase? I forgot the answer for this. Yeah, but that's an issue. But this is I think for people from a high energy background, this looks a little bit strange because as a lattice model, there's no field theory. So there's natural question: what is the low energy field theory for this kind of system? But this duality helps. Suppose the edge is gapless, is due to this axion model. So the low energy field theory is just a conformal field theory of C equal to 1. That's a Gaussian theory. And so therefore, the Gaussian theory is actually given by this. So we have a two field in boundary. So this is really in the Carroll-Boson language. We have two Carroll-Boson field on the boundary. And it's Carroll-Boson because we have a little bit unusual kinetic energy term. We have only first order time derivative. But also, this time derivative term coupled to 1 to 2. Usually you have this partial x phi 1, partial t phi 1. Usually you also have that term. But in this particular case, we don't have that. This kinetic energy only coupled to 1 and 2. Then we have usual potential energy, just the square of a gradient of the field. So this is this particular Carroll-Boson theory actually is an effective field theory to describe this boundary. And the Z2 symmetry is in this series pretty simple, just exchanging two field, the two field exchange. And this is exactly what I mean, is that this field theory with this kind of Z2 symmetry is anomalous. In the sense, Z2 symmetry is anomalous. So if you put this field theory on the lattice, then you'll find that this Z2 symmetry has to be non-on-site. Or another way, this Z2 symmetry cannot be gauged. If you gauge it, you get anomalous Z2 gauge theory in 1 + 1 dimension. So this is a kind of, I don't know, it's global anomaly of Z2 symmetry or something. And in this formulation, one can choose a different field. And certainly in this formulation, this field choice is natural because these phi 1, phi 2 are independently compact. So these both have a 2 pi period. But if you don't worry too much about this 2 pi period, then we can choose another basis, this phi plus, phi minus. And then this field Lagrangian can be diagonalized in this phi plus, phi minus spaces. But however, the compactification is not diagonalized in this new field. It's more complicated. But in this phi plus, phi minus spaces, it's clear that we have a right mover plus and the left mover is a minus. But then you can notice that under exchange, only phi minus carries Z2 charge. Phi plus do not do anything, do not change under Z2 transformation. So that's precisely we have a situation that only right mover carries Z2 charge, left mover do not carry Z2 charge. So that's why this, from field theory point of view, it's pretty clear this Z2 symmetry is anomalous. Yeah.
Well, my question has two versions. The first formula for H right and H left, that corresponds to a particular radius of the circle.
Yes.
So one question is, how did we compute it? And the second question is it the free fermion radius or something along that markup?
I think so.
Well,
But let me put it this way. Maybe I rephrase your question the following. You may ask how I derive this edge theory. How do I know this edge theory is that one? So actually, this is the green part. So this is the numerical calculation of this XY model. This is a spectrum. Because XY model spectrum have these conformal towers. And then because we know this very special Z2 transformation, so therefore we can study how this XY model conformal tower changed under this very particular Z2. So then you find it change this way. So this is how they change. So this L and M is just a two index to label different conformal towers. And then the claim I didn't present here. The claim, these are real things. Those are real data. Then we have to show that this particular effective theory reproduce this kind of results. Yeah. And so that's one way to derive it. Another way to derive this is to using this mutual chain summon theory in the bulk. It's a field theory description for the Z2 SPT states. Then you can use then using mutual chain summon theory, you can derive these edge states. And this may be more direct. Yeah. But the more elementary way is that to study this XY model and their symmetry property, then using this data, numerical data, try to infer this field theory. So that's what we do. Okay, so these are just two examples. So I discussed two examples of this SPT states. One is a Haldane phase in 1+1 dimension. Another is this Z2 SPT states, a CZX model in 2+1 dimension, and related physics. And so now I try to present a general theory for this kind of SPT state. And the purpose of this general theory is that we want to have a systematic understanding of all the SPT states in all dimensions. Can we have some understanding at that level? And the answer is yes, actually pretty simple. And so this general theory is that first this general theory is for any dimension, so we can have space-time can be any dimension. And we can have any group symmetry, so we have a symmetry group, which is any group. Okay, so therefore it's natural to think about a nonlinear sigma model based on this group symmetry. So we consider a nonlinear sigma model, a field theory. The target space is a group, is our symmetry group. So then we can build this nonlinear sigma model of that. And then the easiest nonlinear sigma model is just this, just some gradient term, square, and with a coupling constant. Okay. The symmetry is realized in a particular way. You only have a so-called, I don't know, it's a left-hand symmetry. H only acts from the left. So this is how symmetry acts. Not the other one. You know, another definition is H inverse on the two sides. We don't do that, so we only do this. Okay. So this is how symmetry acts. Then clearly, if lambda is very small, then the gradient term would cause big energy or big action. The G want to be constant. So the ground state would break the symmetry. So the average of G is some constant. If lambda is very, very large, then the cost for the gradient of G is very small. So G have very strong fluctuation in the space-time. Then you may go into disordered state. So there's a phase transition from small lambda to large lambda. For large lambda, the ground state are disordered, and you may average of G equal to 0. So that is the picture. Okay, and so from RG point is that if lambda is pretty large to start with, we'll go to a larger energy scale. The lambda would become larger and larger and go to infinity actually. So when lambda flow to infinity, this action S is very simple, it's 0. You know, so the fixed point theory for disordered phase is very simple. Just action equal to 0, Hamiltonian equal to 0. Yes.
How does this interval make sense when you have G discrete?
What?
When G is discrete.
We don't worry about at the moment. But later I will worry about that. But you can imagine now we assume G is continuous. So yeah. And so that sounds like a study topological theory. You know, S equals 0 is our starting point. And there's no simpler theory than S equal to 0 theory. So basically, the study of SPT states is a study of S equal to 0 theory in some sense. Okay. Yes.
The question is not just if G has to be continuous, but it has to be connected. When you have a group of disconnected components, it has to have only a single.
Oh yeah, that's right. Yeah, if a G have a disconnect component, there's almost like a discrete part. Yes. Yeah. But you know, at the moment I just want to give some ideas, some pictures, so don't worry too much about those details. But later we'll fix all those technical points. Okay. And so certainly the biggest question is that S equals 0 sounds really trivial. You know, how come you have a different SPT phase? You know, SPT phases are disordered states, no symmetry breaking. You know, how come you have this? You have a different SPT phase from S equal to 0. And, but however, these different SPT phases can come from different topological terms. So let's consider a modified theory. And we can add a topological term. Okay. And this topological term can exist if a space-time dimension pi, the d plus 1 space-time dimension is a pi d plus 1 of the G is non-trivial. Then that means the space-time can map into the G, can wrap it, have a winding number. And then you could, so this W basically is an integer times its winding number. So W always integer. Then we add this 2 pi I times integer. I think, no, not this integer. I'm sorry, I should say this. The integration of a W, I should have a spatial integration as well. The integration of a W is always a k times integer, this winding number. For example, in one dimension, sorry, in 0 plus 1 dimension, we have U1 group. U1 group is as S1. So the pi 1 of S1 equal to Z. So therefore, we can choose our W to be this G inverse partial G with a coefficient K and etc. And you will see that this integration, sorry, this is right. In 0 plus 1, this integration is always a K times integer, which is a winding number. And say in 2 plus 1 dimension, we can choose G to be SU2 group, which happen to be S3, 3 sphere. And then pi 3 of SU2 also Z. Then we have something more complicated. We have this kind of a combination and to give us this W. This W have a similar property that their integration over space-time always a K integer times a winding number, which is also integer. So this is always integer. So therefore, adding this topological term is do nothing, because our path integral only depend on this e to the minus s. But this term is always 2 pi. So it's 2 pi I. When you do 2 pi I, the action amplitude do not change. So So this is a new nonlinear sigma model with additional topological term. And people realized this a long time ago. We know this. And I remember in the 80s, when think about this, say 2 pi I means nothing. So 2 pi I with 2 pi I and without 2 pi I is the same thing. So we say this term have no physics, so we just drop it. Now thinking back, I should drop it. Then we can understand SPT in the 80s. And so the key point is that although this term have contributed to nothing to the path integral, if the space-time is closed, this term is still non-trivial. Okay, and so if we believe this term can be non-trivial, then the thinking is following. Well, because this term do not change dynamics, so this lambda still flow as before. So this state, when lambda is large, this action still describe disordered states, and then in the infrared limit, the lambda flow to infinity, and this term is gone. So the fixed point action is a pure topological term. In last transparency, we say when lambda go to infinity, the fixed point action is 0. So now in this transparency, we say when lambda flow to infinity, the fixed point is a 2 pi quantized topological term. And the 2 pi quantized topological term do not affect path integral for closed space-time at least. So, and then the claim is that this 2 pi quantized, yeah.
Xiao-Gang,
Yes.
before you leave the last slide, I want to point out from the intense matter point of view
Yeah.
that exactly this phenomenon is what we have in the field theory of the integer quantum Hall effect, not in the sigma model for that, which has the theta term.
Oh yeah, that's right.
And the different values, the different multiples of 2 pi are the different integer quantized Hall states.
That's right. Yeah. So in the disordered this model. Yeah. But there's a chiral central charge somehow. Yeah. 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 But actually, I think also maybe in 90s, Tai Kai-En actually have a nice paper, which is about, the point of the paper is that this 2 pi quantized term is non-trivial. It provides gapless boundary states. That's the reason to have a gapless boundary states. So he actually studied this model for SO3 case, that's a Haldane phase. So that paper already say that this 2 pi quantized term is meaningful and actually is responsible for the spin 1/2 at the boundary. And so there's another chance in 90s we can pick that up and develop this cohomology theory. And again, we didn't do that. And but however, the point is that this 2 pi quantized topological term turns out to be important. So now we just say they are important, and we don't say it's trivial. We say they are important. If they are important, then we try to say that this different fixed point theory actually is a different 2 pi quantized topological term. And this different 2 pi quantized topological term corresponds to different symmetric phase. So if you think they are important, you will say this different topological nonlinear sigma model, basically different 2 pi quantized topological term correspond to different disordered phase. Yes?
What's funny about your explanation is that in the disordered phase, G and the sigma model aren't good variables or good descriptions.
Exactly.
So possibly a gauged version of this would be clearer.
Maybe, I don't know, yeah, I don't know the gauge version, but
Gauge version, I believe, would be.
This would be really interesting. This is actually the key. That's actually this part. And we can talk about it. Maybe gauge version can fix this problem. But what I'm going to talk about is using a lattice version, but still nonlinear sigma model to fix this issue. Yeah. And but the point of view is that the different 2 pi quantized topological term correspond to different symmetric phase. This is the this is the main point. And then what do you mean by different 2-pi quantized topological term? Then we have this funny notation. And so this home is a set. So each element of this home is correspond to a quantized topological term. So this mathematical symbol kind of classify different 2-pi quantized topological term. So the interpretation is that this pi g is a abelian group. No, not I think in higher dimension is abelian group. And then this home, I don't know what this home really means, but here I mean linear map between z to z. So basically linear map between z to z. So actually, this is a very, very fancy way to say my topological term has this k coefficient. Different k coefficient means different linear map. So this home just this k coefficient. It's a very fancy way to write down this k coefficient in the topological term. But anyway, it's a home. It's nice. And then the reason I want to write a home because I want to say that this home is wrong. And the right answer is H. It's still home. So this is the wrong answer. Actually, the right answer is really this one. And the why is that? Is because this point. Just bring up. When lambda go to infinity, this field G fluctuates like a crazy. You know, the gradient have no cost, so gradient will be infinite. If you have a cutoff, if you put in cutoff, that means the G at one point and the G at another point are totally uncorrelated. They can have arbitrary fluctuation. So what I really try to say is that G have no continuum limit. If you start with cutoff theory, G have no continuum limit. If G have no continuum limit, it's not continuous function, it does not make sense to talk about this mapping class. This mapping from space manifold to G. That's a continuous map. So pi refer to continuous map. And we don't have such a notion of a continuous G function. So therefore, whole thing class doesn't make sense. And so really, when lambda goes to infinity, it's a fixed point. So our field theory just collapses. Don't make any sense. And however, the point is that even though the techniques, formalism collapse do not make any sense, but the idea, the spirit, still correct. So this idea that the different fixed point theory or different 2-pi quantized topological term correspond to different symmetric phase. This idea survives. And so what we need to do is that to develop different mathematics so that so to implement this idea in a more correct way, not using field theory, but using something else. And what I'm going to present next is we try to put this nonlinear sigma model on the lattice. And we try to ask, when you put the nonlinear sigma model on the lattice, do we still have this 2-pi quantized topological term or not? And then you say, you cannot have it because on the lattice, there's no continuous map. There's no topology, nothing's there. But actually, surprisingly, there's something there. And the way to define topological term, to define mapping class group on the lattice, this lattice version of this kind of theory actually is a group homology theory. So group homology actually is pretty simple. It's just trying to define this 2-pi quantized topological term on the lattice, and nothing more than that. We just try to do that on the lattice. And to me, it's amazing it's doable on the lattice. But at a physical level, it's pretty simple. Just try to define this 2-pi topological term on the lattice. And I just mentioned that maybe whether there's a gauging it can be another way. Not using lattice, but using gauge a field theory. I'm very intrigued by lattice talk. And maybe one don't need to go to lattice. Maybe there is a way to do that within field theory and still fix this problem. But indeed, there is a problem need to be fixed. And within nonlinear sigma model, so what I'm going to do is do some lattice version of nonlinear sigma model. Okay, any questions here? Yes.
Does this turn out to be the same as what appears in digraphs classification?
It's a little bit different, but later I will describe the connection. Yeah.
So at this stage, at least based on these examples, it's not clear why you want group cohomology. You could just be using cohomology of the group manifold in the conventional sense, like Girard or the G1 coefficients. G inverse to G cubed is clearly defining a cohomology class.
Yeah. I'm not so sure because if you do that, you are doing the so-called topological cohomology theory on the group manifold. And here I'm doing group cohomology of the group, which is a topological cohomology on the classifying space of the group. So, so there's a.
My point is, which is a naive one, is simply that the action that you have there in the middle of the slide, although it's only one example,
Oh yeah.
this just looks like ordinary cohomology.
It's like ordinary cohomology on the group manifold. Yeah, and but that notion is not quite right. Yeah, and it turns out that some kind of cohomology on the classifying space happen to be the correct answer. And yeah, SU2 is right, but for the U1, for example, for the U1, the H3 U1 with U1 coefficient is non-trivial. But using nonlinear sigma model is very difficult to see. But the U1 group manifold is a one dimension. Yeah, that's hard to see. So maybe let me finish with this. And so how to do this? How to put things on the lattice? It's not so difficult. So first ignore this Sijk. We just triangulate space-time. And then we say that on each triangle, we do this action with the integration of L on this triangle give us amplitude. So this new Gijk is just the amplitude for each triangle. This Gijk is a group element live on the vertex. So we kind of some discrete version, we say, so basically this choice of this new Gijk it's like choice of Lagrangian. We say we have a Lagrangian whose integration on the triangle is given by this function. That's it. And then certainly the path integral is that we have an integration of L over all space. That means we should multiply this new together over all space, over all the triangles. So that's this product is multiply all the new together on all space-time. Then we sum over, so that gives us this action amplitude. Then we sum over G, we do path integral. That's defined the nonlinear sigma model, and that's it. So that's how we discretize the nonlinear sigma model. We put the group element on the vertex, and then for each vertex, we directly write down this action amplitude. That's new. That's an action amplitude for each triangle. And then we multiply this triangle together, give us total action amplitude. Then we sum them over, we get a path integral, partition function. And that's how we do it. But there's a little bit technical issue. Is that we want to write down our Lagrangian locally. So basically, if you give me a triangle with a 3 index, then I can write the action amplitude for this triangle. So we can do that. But however, there's a technical issue. That's which one is the first index? You know, this I, J, K, you know, which G appears the first, which G appears the second, which G appears the third is a little tricky because if you have a triangle with a 3G, then if you look at them individually, you don't know which one is first, which one is second. So you are very tempting to write down the action which are totally symmetric respect to these 3 index variable. And that seems to have a symmetry of this individual triangle. But that's too constraining. It's not good enough. So it's important to add so-called branching structure. And so we add the arrow to each edge. So that this triangle have this have frustrated. So you can see these 2 arrows go this way, but the third arrow would go against it. So this kind of frustrated way to putting arrow on each triangle is called a branching structure. So we put this structure in our triangulation. So when you do that, then each 3 vertex would have order because this vertex have no incoming edge would be the 0, first one. This vertex have a 1 incoming edge, that would be second one. This vertex have a 2 incoming edge, which is the third one. So now we have a 1, 2, 3. So that's 1, 2, 3. So it's naturally ordered. And then we also have a sense of orientation. You can see this vertex, this dominant orientation is going out the board. And this triangle, the dominant orientation would right hand will go inboard. So this plus orientation is a negative minus orientation. So this orientation. Then we say that the actual amplitude is this function we associate for each triangle. But depends on orientation, sometimes we have a dagger, sometimes we don't have a dagger. Sometimes we take complex conjugate, sometimes we don't take complex conjugate. So this is our way to design the nonlinear sigma model on the lattice. And that's it. So with this technical complexity, we just design this nonlinear sigma model on the lattice. And every time we choose the new Gi, choosing the different new, like choosing different Lagrangian, like choosing different theory. Okay. And certainly we should choose this function nu to have a symmetry because we want to have a symmetric nonlinear sigma model. So we require this function to have this symmetry condition. Okay. And then now next question is following. Suppose we are in a disordered phase. And so what kind of nu give us disordered phase? The answer is very simple. If you take a nu Gij equal to 1, do not depend on G. That's a disordered phase because this choice corresponds to taking S equal to 0. So all the function is just equal to 1. So if you choose a nu equal to 1, that's disordered phase. But then using our previous idea is that there's maybe new disordered phase. That nu is non-trivial. But somehow this action amplitude is always equal to 1. When you multiply them together, you get 1. So this is what I mean by 2 pi quantized topological term. That is on the closed space-time manifold, all the paths have amplitude equal to 1. So that's correspond to, we pick some non-trivial nu. So that's when you multiply all these triangle together on the closed manifold, it's guaranteed to be equal to 1. So this kind of choice of a nu would like a 2 pi quantized topological term. So can we find such kind of nu? Then the answer is yes. Because in 2 dimensions, so here I'm talking about a 2-dimensional example. In 2 dimensions, the simplest sphere is a tetrahedron formed by 4 triangles. So that is simply the space-time sphere. So at least can we find a nu such that on this simplest space-time sphere, this partition function equal to 1. So then let's give this condition. So because here we say nu always a pure phase, so I can replace a complex conjugate as the inverse. So I do this. Okay. And so this is and so we want to find the nu has satisfy this condition. And when you satisfy this condition, then at least on the simple sphere with 4 triangles, the partition function always equal to 1. And the action amplitude always equal to 1. So amplitude for each path always equal to 1 once you have this condition. And that's it. So this is the group cocycle. So basically, what is group cocycle? Group cocycle is a function. This function is group cocycle satisfying these 2 conditions: a symmetry condition and a cocycle condition. So the function satisfy these 2 conditions is a group cocycle. We call 2 cocycle, and that's it. So there's nothing fancy about it. Just solution of this equation. And actually, this solution can be non-trivial. Depending on group, there are non-trivial solutions. And this non-trivial solution would give us non-trivial SPT phase. And that's almost it. There's a few little technical things. Maybe I will do that in the next lecture. But the basic idea is here. Just we can indeed find some function nu such that on the closed space-time manifold, their multiplication always equal to 1. And this kind of function or this kind of group cycle would correspond to non-trivial 2-pi quantized topological term, and the corresponding theory will correspond to realize this SPT phase. Yeah, that's basically the idea. Okay. Yeah.
What's the physical, like, what's the physical meaning of this co-boundary condition? Like, because you're calling these two phases equivalent, and it comes from the original definition of there having no phase transition between two. So how can I see that when this, like, these two
Yeah.
cycles are related?
So that's a topic of next lecture. But anyway, since you asked it, I want to say another way to say, not from this co-boundary point of view, is that this is nonlinear algebraic equation. It's like in this case, it's a quadratic equation. So this quadratic equation sometimes have many, many solutions. So there's a space of solution. And then there's an issue. The space of solution may be connected. So one solution, another solution can be smoothly connected into each other. When that happens, we do not call they are different phases. So therefore, but however, this solution space may have a disconnected component. Another part which do not connect to this part. This disconnected component may correspond to different phase. So therefore, this group homology is actually another way to say it's a pi zero of the solution space. So how many components of the solution space of this nonlinear algebraic equation? If a pi zero solution space is non-trivial, this pi zero is denoted as this. You can use pi zero is this way. And then that you have a quantized, so that's a distinct quantized 2-pi topological term. And this distinct quantized 2-pi topological term corresponds to different SPT phase. Thank you for the question. Yes?
Can this also handle space-time symmetries like time reversibility and parity?
Yes, and for the parity, we tried, but not very hard. For the parity, you can see that you have to really changing this triangulation and the branching structure. So parity may correspond to permuting those index. So when you have parity, not only so parity is Z2, and not only have the Z2 action, but then you require symmetry condition is that those index permuted. So you have different symmetry condition. Yeah, there's a half-baked project working this. I don't know what is the result at the end. But you can imagine this kind of multiplication probably can include some kind of point group of space-time symmetry.
Also, does this reduce to the AKT model or something like that for 1+1?
No. It's reduced to the, but this is the Parsinical space-time version. If they reduce to anything, it's reduced to this reduced to this version. This is spin 0, spin 1 version. So AKLT is for spin 1. So if you include spin 0, you get this 2 spin 1/2 per site. This is a true fixed point theory. So this the fixed point Lagrangian I'm talking about correspond to this 2 spin 1/2 per site model. Yeah.
Any more questions?
Yeah.
So at the end of the very last slide, you had come out with H2G1. So this is the same one that shows up in green when you're talking about projective representation?
Yeah, that's also the next, probably the, yeah. So here I do, to draw a picture, I do 1 plus 1D. So 1 plus 1D is turned out to be H2, which is the projective representation. But you can imagine this kind of formulation can be easily generalized to any dimension. If you do this kind of thing in other dimensions, certainly this condition are changed. But then the similar idea give you H3, H4, and etc. And so the physics are different, so maybe we'll discuss that next lecture. But this, yeah.
Okay, maybe we'll take one more question.
How do I say that the largest theory is that discretized non-linear sigma function?
Okay, at this stage, the G don't have to be continuous. Actually, this version is better for G to be discrete. If G is continuous, this is a function. We don't know how to handle that. That's much more complicated. If G is a discrete finite, this is just a tensor of a 3 index. You have finite number of unknown, you can solve this. So this version works better for discrete G. Actually, for continuous group, this description group homology is very tricky. Actually, we don't know how to handle this very precisely. There are some hand waving thing there. Yeah.